Thanks very much. I'm trying to withdraw from PowerPoint, but it does serve its purpose. If you don't want to look at the screen and you want to actually write something down, you all should have a copy of this set of notes, which is basically a printout of that particular item. And what I want to do today, I'm going to reinforce what Allison said, because there's just way too much good stuff on this topic to possibly cover in a day, let alone 15 minutes. So what we've done is we've put all of this stuff on her website. There's additional stuff on my website, dozens of articles, so you can focus in and grab what you want. And our particular way of doing things is to look at the scientific method. In other words, we're not going to allow politics to influence our decisions. We're going to look at the basics of physics, chemistry, and that kind of thing, and just see where that leads us. And the different approach that we like to emphasize is to look at the entire cradle-to-grave picture. Instead of looking at a battery vehicle maybe is clean when you run it, but where does all that electricity come from? Are we burning more coal than we would have otherwise? And that kind of thing. And the short term that we use here is LCA, life cycle analysis. Think of that as meaning basically cradle to grave, okay? Jenna? We'll look at these fuels. Now, the references that you have available on the websites include these and many others. But what we want to do is two things today. We want to look at these fuels quickly, come to a conclusion about the fuels, and then look at what happens when you burn those fuels in certain kinds of vehicles, because it's not only just the fuels, but what you do with them. And that's the big picture. But we'll start with the medium-sized picture of fuels. Next, please. This is our baseline, and our baseline is basically the fuels that we have today. And we're going to take a look at what the numbers are from a life cycle analysis point of view for fossil fuels. Now, LCA, in its classic sense that we developed, looks at energy. So energy in versus energy out, but it also looks at pollutants, and the criteria pollutants as well as CO2 are of interest today. But we also are going to look at water. It turns out that water is something that you guys need to be aware of as we go down the road. We don't want something like corn ethanol that takes a lot of water when we don't have any water to spare. And then we finally look at land use. In other words, how much land do we actually use for these various kinds of fuel plants? Next. So here's an example. This is a fossil fuel idea invented by the Germans. They basically had some gas. They needed liquid fuel. So 60 years ago, they figured out how to make that happen. And that's the basic principle of that process is unchanged. So we can make liquids from gases. We have a lot of natural gas in this country, so that might be a way to do it. And I'm going to let you just look at this very quickly. I'm not going to read these slides to you, but hit the key points there, particularly the kind of indirect emissions that we are talking about and so forth. Another fuel we're going to look at, and I should say, I'm going to repeat this one more time, that each one of these slides has a whole scientific paper behind it that you could get, you can look at. It'll tell you what oil shale is, where it is, and how you make fuels out of it. Oil shale is a very diffuse energy source, and it's, if you just look at this bar chart, you see that it comes in well below your Wheaties. The breakfast cereal has a certain amount of energy in it, but oil shale is about a third of that. So that gives you an idea that you're going to be handling a hell of a lot of materials to get a modest amount of fuel, okay? Tar sands you've heard about. This is what it looks like up in Alberta, a polluted lake. The strip mining is environmentally very damaging. It uses a lot of land, a lot of water, and we factor all those numbers in to the life cycle analysis for tar sands, okay? Well, let's look at some non-fossil fuels. This is ethanol. And ethanol, of course, we've all heard about. The ethanol era is pretty much over with because it was not looked at scientifically 5 to 7 years ago when we had all the science. We knew how much water it took for ethanol. This map on here is one of a number that appear in my various papers, but this shows you where you can produce ethanol. And the darker the color, the more production level with irrigation. There's a huge amount of water involved, and we'll talk about that a little later when we see a summary of all of this. But basically, the corn ethanol problem, it's too land intensive, too water intensive. It uses more petroleum to make ethanol than if you never thought of making ethanol, and on. The CO2 burdens, the carbon burdens are higher with ethanol than without, and so forth. And again, all explained in detail elsewhere, okay? So let's let corn ethanol go and look at some other forms. Switchgrass you've heard of. That's what it looks like. Next. And these are some other crops that we can produce biofuels from. And basically, the middle column is in conventional units. So people talk about how many gallons per ton of soybeans you can produce. And then in the right-hand column is the key number, which is the amount of energy you produce per acre. So that is easy to convert into the land area that you're going to need. Next. Algae, we want to talk about it in a little bit more detail. It's basically algae that you know of. There may be some difference in the biological makeup of the algae species that we look at, but it's a source of the raw material for making biodiesel. And it's one of the more promising ones because the land requirement is small. There's essentially no water requirement even comparable to ethanol or any of those water-consuming approaches. And next. Thanks. This is what some of the reactors look like. And they're basically, the oldest one is in the lower left-hand corner. And that's basically just plastic tubes exposed to the sun, and you have algae growing in water. And the water, of course, can be reused and recycled. In the lower right-hand corner, you see a bigger installation. But the real deal maker with algae is that it grows like gangbusters if you feed it CO2. We're trying to get rid of CO2. So here's a big CO2 sink. Hook it up downstream of a big power plant, and you see the number from the previous slide basically tells you how much land you need for a 1,000 megawatt power plant. So this is a great synergism. The productivity level goes up, the cost is marginal, and so forth. The next way to produce some liquid fuels is to look at garbage, municipal solid waste. And it turns out that that is a huge resource. And we're also helping out with our big landfill problem because we're not going to be dumping everything back into the ground, but we're actually going to convert it into a liquid fuel. And this can be either ethanol or biodiesel. Next. And you can read this one for yourself. I think we skipped, let's back up one, Jenna. You have a chance to see that. Okay, so there you go, that's good right there. Notice the second bullet, we don't have the big land imprint that we have to deal with biodiesel, for example, or with ethanol.